Archimedes' principle. A mug of water appears lighter to lift when it is underwater and appears heavier when lifted above the water surface. When a solid object is submerged in a stationary fluid, the fluid exerts an opposing force in the upward direction on its surface. This net upward force is called the upthrust or buoyant force. In other words, a fluid provides partial support to any objects placed in it. Therefore, an object attached with a spring balance, when suspended in water, experiences a decrease in weight. Further, if the object is fully immersed in water, its weight can be recorded as its lowest weight. This change in weight is due to upthrust, that is, the buoyant force by the surrounding water. If we repeat this activity in a different liquid, the loss in weight of the object comes out to be different as compared to water. It indicates that when an object is immersed in a liquid, its weight is reduced, and that depends upon the density of the liquid as well as the height of the object placed under the liquid. However, the buoyant force is due to the gravity acting on the fluid. It has its origin in the pressure difference occurring between the top and bottom of the immersed object. Let us take a cubical block. When it is immersed in a fluid of density ρ, the surrounding liquid exerts normal forces on all of its faces. Clearly, the horizontal forces being equal and opposite cancel out each other. But the vertical forces acting on the top face and the bottom face of the object are not the same. Since pressure in a liquid increases with depth, therefore, the pressure at the lowest face is more than the pressure at the upper face, and the difference is equal to the pressure exerted by the liquid column of height equal to the side of the cube. And thereby, the upward force acting at the lower face is more than that of the upper face, as can be seen. This difference in forces gives rise to a net upward force, which is the buoyant force acting on the cube. In general, if volume V of an object is immersed in a fluid of density ρ, the buoyant force can be expressed as U equal to ρgV. Here, volume V may be the total volume of the object or any fraction of the total volume. This precise value of the buoyant force has some significance, because it is the same as the weight of the liquid displaced by the object. The result holds true irrespective of the shape of the object. Archimedes summarized like this: when an object partly or completely immersed in a fluid experiences an upward buoyant force equal in magnitude to the weight of fluid displaced by the object. Let us verify the Archimedes principle in a simple way. Suppose we focus our attention on the imaginary cube formed with liquid in the liquid container. This cube of liquid is in equilibrium under the action of the forces on it. One of these forces is its weight. Apparently, the rest of the liquid inside the container is holding it in equilibrium. Thus, the buoyant force on the cube of the liquid is exactly equal to magnitude of the weight of the liquid inside the cube. Now, imagine that the cube of liquid is replaced by a cube of steel of the same dimensions. What is the buoyant force on the steel? The liquid surrounding a cube behaves in the same way whether a cube of liquid or a cube of steel is being buoyed up. Therefore, the buoyant force acting on the steel is same as the buoyant force acting on any cube of same dimensions. Let us say this activity. When an object attached with a spring balance is suspended in water, it experiences a decrease in weight, which is equal to the weight of the displaced water. Similarly, when the object is suspended in liquid, it experiences a decrease in weight, which is equal to the weight of the displaced liquid. Hence, apparent loss in weight of the body is equal to the weight of the liquid displaced by the body. Therefore, the Archimedes principle can also be stated as the loss of weight of a body partially or fully submerged in a fluid is equal to the weight of the fluid displaced. For a floating object immersed in a fluid, partially or completely, the weight of the fluid displaced by the object is equal to its own weight. Hence, the density as well as the volume of the object, the density of the fluid, play an important role to decide whether the object will float or sink. However, while calculating the buoyant force on an object, the shape and position of the object also plays an important role. For example, a ship made of iron floats in water because of the weight of the water displaced by it is more than its weight. It is designed in such a way that its bottom is broad and it increases from bottom to a certain height. Due to this special structure, a ship or a boat disperses a large amount of water. In equilibrium, the weight of the ship and its content is equal to the weight of the displaced water. But a piece of iron sinks in water and floats in mercury due to the different densities of the two fluids. Let us have a look on the condition of floating bodies. When we drop a metal block in water, it sinks, as density of the metal is more than the density of water. Or in other words, weight of the metal block is more than the buoyant force and resultant force is a downward force. But when we drop a plastic block in water, it gets completely submerged and floats, as density of plastic is equivalent to the density of water. Or in other words, weight of the plastic block is equivalent to the buoyant force and resultant force is 0. If we drop a wooden block in water, it floats, as density of the wood is less than the density of water, or in other words, weight of the wooden block is less than the buoyant force and resultant force is an upward force. In other words, if the density of the immersed, homogeneous and solid object is more than that of the fluid, the object will sink, as the weight of the body is more than the upthrust. While the body will float if the density is less than the fluid, as the weight of the body is less than the upthrust. That is why an iceberg floats in the seawater, as the density of iceberg is 0.9 gram per centimeter cube and the density of seawater is 1.02 gram per centimeter cube. Rock has more weight than the water, thereby sinks in the water. A type of stone known as pumice floats in water. Do you know why? Pumice has a large number of holes, because of which upthrust on it becomes more than its weight. Let us see an interesting activity. A can of normal Coke sinks in water, but the can of Diet Coke floats. Because the density of normal Coke is more, while that of Diet Coke is less than the water. Similarly, a hot air balloon rises in air because the density of the warmer air inside the balloon is less than the cooler air outside the balloon. In other words, the cold air displaced by the balloon is heavier than the weight of the balloon, and a buoyant force acts on the balloon. A balloon tends to fly better in the morning when the surrounding air is cool. Hydrometer is a device used to measure the density of a given liquid. It also works on the Archimedes principle. Let us take 3 beakers containing olive oil, salt solution, and water respectively. Hydrometer is placed in each beaker, which measures the density of the liquid. Sinking of hydrometer shows the density of the liquid. As in case of olive oil, it sinks the most. That is, buoyant force in olive oil is less, therefore density of olive oil is also less. It sinks the least in salt solution. That is, buoyant force in salt solution is more. Thereby, density of salt solution is also more. Let's try some problems. Measure the buoyant force on a helium balloon with a radius of 35 centimeters in air. If the density of air is 1.9 kilograms per meter cube. Here, radius of the balloon is 35 centimeters or 0.35 meters. Hence, the volume of the balloon is 0.17967 meter cube. This is also equal to the volume of air displaced by the balloon. Since the density of air is 1.9 kilogram per meter cube, hence the buoyant force on the balloon, which is equal to the weight of the air displaced by the balloon, comes out to be 3.345 newtons. Next problem is, what is the minimum volume of a block of wood if it is to hold a 45 kg boy entirely above the water when he stands on it? Density of the wood is 850 kilograms per meter cube. Weight of the wooden block is equal to the product of its volume, density and acceleration due to gravity. Weight of the boy is 45 g and the upthrust, that is the weight of the displaced water, is equal to the product of the volume of the wooden block, density of water and acceleration due to gravity. According to the Archimedes principle, the weight of the buoy and the wooden block must be equal to the buoyant force on the just barely submerged block. This gives the volume of the wooden block as 0.3 meter cube. Let us try another problem. A balloon having a mass of 450 kg remains suspended motionless in the air. If the air density is 1.29 kilograms per meter cube, then what is the volume of the balloon? According to Archimedes' principle, upthrust is equal to the weight of the balloon, which gives volume of the balloon equals to 348.8 meter cube. In our next problem, find the percentage volume of an iceberg submerged in seawater if the density of ice and seawater are given. If V is the volume of the iceberg and V0 is the volume of the immersed portion of the iceberg, then according to Archimedes' principle, the weight of iceberg is equal to the weight of displaced water. Therefore, ratio of submerged volume and total volume is equal to the ratio of density of the iceberg and the density of seawater, and percentage volume of the iceberg submerged in sea comes out to be 89.3%.